Okay, good morning, ladies and gentlemen. Thanks to those of you who are here in the hall and the great turnout, and welcome to the members that will be online. And we wish you all a successful and healthy 2026. I'd like to quickly introduce our speaker for the day, who's Mr. Bruce Engelsman. He's a principal engineer with SRK. Bruce is a civil engineer with 29 years of experience in environmental and engineering studies, design, and implementation. He completed a BSc in civil engineering at the University of Cape Town in 1994 and is a registered professional engineer and construction project manager. He specialized in civil geotechnics, nuclear siting geotechnics, waste management, particularly tailings, mine closure, land contamination remediation, and flood management risk, which is quite useful given where we live, particularly those of you from Stanford. His expertise includes project management of technical and surface water projects, geotechnical investigations and design, including onshore civil geotechnics and shallow marine geotechnics, in other words, harbors, numerical modeling, land rehabilitation, remediation design, flooding and flooding risk management, road design, and 3D AutoCAD design. And I can carry on, but far better we get Bruce up here to talk about what he's going to talk about today. Thanks, Bruce, for making time, bringing the family, and we look forward to your presentation.
Okay, maybe if breakfast wasn't enough of an icebreaker, maybe just a word on how I got here today. Henny at the back there did quite a lot of work with some key people in SRK, mainly Oscar Stefan. Back in the day, he's the S in SRK. And that's how they got to contacting SRK when we provided a little bit of funding to the OGG. Then another interesting story, there was a guy that worked at SRK by the name of Dave Ortlip. And the Bristows and the Ortlips have been very close family friends for some time. And my wife, who's here with us, went on a fishing trip with me and Dave Ortlip back in the day to the Bristows farm in the Free State Islands. So it's funny how the world is such a small place, but there are a few people in the room. I used to do quite a lot of work with Malcolm for PPC and De Hoek. So yes, the world is a small place. Right, let's get on to the talk and no more waffling. All right, so this talk actually is a bit of a hybrid from a lecture that I gave to the South African Institute of Civil Engineers last year. To the geotechnical division of SAICI. And I've tried to truncate it a little bit to make it fit into the time we have here. And we'll see how it goes. I'm going to be watching the time closely. If I'm running out of time, I will speed things up. I am a little bit monotone, so if anybody has any questions, you may stop me because it helps to break the monotone, and we'll answer the questions as we go. But essentially, I'm going to be taking us through the three main rock types, and I'll give a little bit of a case study in projects that I've been involved in, particularly on how the geological setting influenced the geotechnical outcome. And this came about mainly because as I got involved in the tailings industry, I realized a lot of our young engineers knew a hell of a lot about tailings and the mechanics of tailings, but we're forgetting about the geological setting, and it was tripping them up in certain respects, and I'll explain that. So geological setting, there is not enough time in 20 lectures to go through everything that it entails. So you could be talking about discontinuities in rock, which would be jointing, shearing, faults, essentially weak areas in rock, which has a big influence in geotechnics. I'm facing that challenge at the raising of Clanwilliam Dam at the moment. Very complex geology with a lot of faulting and shearing and jointing and the like, making things life difficult. So you could look at strength, index units, rock mass type, strengths, discontinuities, all influenced by geological setting. In the soils side of things, the soils that are derived from various geology is a significant input. But I'm going to be talking a little bit more about the influence of tectonic history and the basic formation of rocks and how that impacts the influence that geotechnics has on projects. And I will swing back a little bit to some of this stuff over here in the one particular case study that I talk about. Right. So geotechnical engineering, it's basically the civil engineering aspect of rocks and soil, so the strength of rocks and soils. We don't concentrate too much on the mineral side of things. We concentrate on the mechanical side of things, although the mineral side of things plays a role to a certain extent. Right, we're going to get on to it. So a geotechnical engineer, when faced with a project, before we get going, we have to devise a way of how we're going to go and have a look at things, because everything is under the ground. We can't see through the ground. We've got to think about how we're going to go about something. So two Latin terms, a priori and a posteriori. So a priori is literally means from something that comes earlier. And this is something we look at as geotechnical engineers to follow some sort of reasoning as to how we're going to approach something. The main reason being that nobody who's spending money and doing any developments wants to pay for anything that they can't see. And all of the work I do, you can't see. So we struggle to get money to do what we have to do. We never have enough funding to do the exploration that we need to. So we have to be pretty cute about how we go about things. A posteriori is something, literally means something that comes later. So the upper one is something that you try and reason out. That one there is when you've got hard evidence to prove what you're postulating. Great. Okay, so the pluses about an a priori approach, which is looking at reasoning before you start your project, is that you can actually sit down and reason things and not dive into something feet first without thinking it out. The negatives are that the justification is independent of experience, so you don't actually have any hard evidence about what you're postulating. The a posteriori thing, which is something that comes after, has obviously got a great benefit in that you've now actually measured things. You've got laboratory test results, you've got borehole core logs, etc., and you're starting to base things on hard evidence. And this is the big thing in geotechnical engineering. There are a plethora of characters in the industry, and everybody has a different take on what the evidence is presenting. So interpretation of evidence is something that creates a lot of debate in our industry. We're aiming as geotechnical engineers to be over there, which is to present hard evidence about what we're postulating, that how geotechnics will influence projects. So where do we actually sit? We're needing at the outset of a project to start reasoning things. We're trying to aim at looking at self-evident truths, and experience or personal observation is where we ultimately want to get to, but we can't see through the ground. But we do have something called geological setting, and this is something that I've if some of my staff were here today, they'd be saying, "Oh God, here he goes again." But it's essentially something that I found very lacking in the younger engineers. They were totally ignoring the geological setting in their thinking and reasoning. So we actually start off as geotechnical engineers in an a priori way. We look at a project and we try and fathom out where we're going to go, and then we aim towards proving the postulations that we make. So our a priori journey starts as geotechnical engineers, specifically with geological setting. And as I said, I'm going to take you through a couple of case studies to show how this panned out in real projects that I've been involved in. But the first thing to note is that there are some fantastic geological maps. The work that the Council for Geoscience did in years gone by in mapping the geology of South Africa is something truly impressive. For those of you who are geologists in the room, there are the wonders of the geologist. And when I did this lecture to SAICI, the bottom left-hand bit there, I found that there was a little bit of a disparity between engineers and geologists, and sometimes engineers thinking that they were superior. So that was really just a bit of it was a bit of a dig at them to say, right, don't forget about the geologists, because your journey should start there. So there's another example of a geological map. If you think about the size of South Africa, to have gone physically into the field and sketched all of this stuff out to that detail is something quite remarkable. So yes, that's where we start, is a geological map. The three case studies I'm going to present to you are, first of all, or not in this order, but a tailings dam project in the Metamorphic complex on the west coast, a nuclear site development near Cape St. Francis on the southeast coast, and a tailings dam case study in the Bushveld igneous complex, that being a sedimentary example. The other thing that is at our fingertips is a fantastic series of books that was developed by a guy called Brink. And if you just look at the acknowledgements in the leading pages to these books, you'll see that this came from a PhD that was done by Professors Visser and Savage at Wits University, where they started looking at the engineering geology of South Africa and trying to jot it down on paper to help others. It was funded by the Geotechnical division of SAICI, which is the body that I did the lecture for, and the Association of Engineering Geologists. But if you look at the people that were involved, these are some big names if you work in my industry. Jack Caldwell and Joe De Beer were both SRK employees. Jack Caldwell was essentially one of the pioneers of tailings engineering in the world, along with Robertson and various others. And Professor Jennings is a real icon. He stood side by side with some really important people in the geotechnical world, like Norbert Morgenstern from the States, very well respected guy globally. The set of books came out in four volumes. The first volume deals with the South African geological zones that are between 2 billion and or up to 2 billion years old. The next one is 2 billion to 300 million years old. The geology, the areas that are characterized by that geology. Then volume 3 essentially looks at the engineering geology of South Africa, and volume 4 was something that came after and looks at the geological formations and breakup after the drift phases, which is the tectonics I mentioned I'd get to. So these books provide you with a wealth of knowledge. Although developed by these people, there are probably about another 50 or 60 contributors in the various volumes, in the form of case studies, pretty much like I'm presenting today. Very, very useful background geological knowledge exists for us geotechnical engineers. And the whole point of this lecture was to get the young engineers to start looking at this valuable information. So we'll kick off with igneous rocks. Essentially rocks that form from molten volcanic materials such as magma, which form granites, dark lavas, and basalts. So igneous rock, there was a point to me putting up these pictures. Everybody knows Boulders Beach, but if you look at the shape of igneous rocks, it actually has a very serious bearing on how we look at stability of tailings dams. Notice there are no straight lines in this, and if you look at how these rocks form, you can see why. So it's the upwelling of magma that either forms intrusive igneous rocks or extrusive igneous rocks like basalt. So if anybody knows the Lesotho Highlands, you're dealing about that geological unit, or geology formed in that way. My case study is going to be concentrating on intrusive igneous rocks of the Bushveld complex and a tailings dam setting. Right. So I'm not going to mention names of the mines, but this is essentially a series of cross sections that come from stability assessments done for tailings dams. So that's the tailings over there, the grey bit. And this here is the foundation, the natural profile, the geology. That is one particular mine and its tailings complex. This is a completely different mine, probably separated by about 100 kilometers. There's a third and another, all completely different projects. This essentially here is depicting the stability analyses that we run. And that's essentially the sort of slip circle failure plane that you would get if the tailings dam were to fail. In each case, it's slightly different shape. As in the failure plane there. And what I wanted to point out, or what I stumbled across, I entered into the tailings world quite late in my career, mainly because I avoided it. Tailings is a high stress environment, so I stayed away from it for a fair amount of time until SRK was in trouble on a certain project, and I was asked to step in and help. But these are real stability analyses that I saw when I first started on this project. And the thing that horrified me in a igneous rock setting in the Bushveld complex was that the engineers were depicting the foundations as hard rock, weathered rock and soils with these dead straight lines, which just screamed out to me. If you consider the Boulders Beach setting, where on earth are you going to find straight lines in an igneous rock setting? So I knew there was a problem here. And here's a second example. Those straight lines just don't make sense. And if you notice these failure planes that I've been showing on several slides here, they're all dipping down into the natural soil profile. So in all of those examples I showed you, there's a failure plane that comes from the top of the tailings into the natural soil profile. And there's some significance to that, which I'll explain to you now. This particular site that you see in front of you now is a project that I was involved in for one of the largest mining houses in the world. And this particular tailings dam was their highest liability globally. So considering everything, market forces, political, geopolitical setting, whatever you can throw out, the risk of failure of this tailings dam was their highest liability across the planet. So there was a hell of a lot of emphasis on this project. And I encountered these straight lines, which was a little bit upsetting to me. So I dived in and I did some geophysical work. These are essentially cross sections from geophysical traverses. It's called ERT, electrical resistivity tomography. That's the surface of the Earth at the top. And essentially ERT is putting a whole bunch of probes that if you can see the little dots along the ground at the top there, it's a whole bunch of probes that you put along the surface of the Earth, and you measure the electrical resistivity differences between the different probes as they penetrate into the ground, and you try and understand hard rock will have a different ERT signature to something soft, and sands will have a different signature to clays, etc., etc. So you try and fathom out what's going on underneath the ground. The point that I wanted to make here was the straight lines that I was seeing in these stability analyses. When you do something like geophysics, this dotted line here now is the interpretation of what the hard rock profile actually looks like under the ground. So the whole straight line theory immediately out the window with one simple investigation. That over there is a hell of a lot better representation of what igneous rock should look like.
What's the depth profile?
That is about, with my eyes, it's probably about 40, 50 meters. But once again, the photographs, the Boulders Beach, classical Boulders Beach picture of what igneous rock looks like aligns a lot better with what I'm showing you here than the straight lines that my engineers were using in the stability analyses. They were just making assumptions about the foundations, and the consequences for doing that. Another important thing about the the geotechnics integration with geology is how things weather. So essentially fresh rock, when exposed, weathers from top down, because the top stuff obviously gets exposed more than the bottom stuff. So there you have really fresh rock. This is true to any rock type, igneous, metamorphic, or sedimentary. But as you go up in the profile, it's exposed for longer. So you start getting soils on top. You get completely weathered stuff going into highly weathered, moderately weathered, slightly weathered, and fresh rock at the base, which is a characteristic profile in a geotechnical zone. And a very important thing about this, and one of the important things about this, is that it becomes less permeable as you go up into clays or down into fresh rock, and you have a zone in the middle, which is the slightly weathered stuff, which is more gravelly, which is more permeable to water, and you'll see why I say that in a second. But essentially, what it throws up in a geotechnical setting, and when you're integrating with geology, is that there are preferential flow paths that can develop. So this is a depiction of what a preferential flow path would look like if it rained on the surface of an igneous rock setting. But these manifest below the ground as well. So below the ground, the igneous rock actually looks like this. It's just that you have a soil covering, and somewhere below the ground, there are going to be these preferential flow paths that are important to geotechnics. Geotechnics is extremely influenced, and the integrity and stability of geotechnical components are extremely influenced by water. Remembering that is the more permeable zone. So the high liability case that I was speaking about, we started out with failure planes that looked like that. They were dipping down into the natural soil profile because of the assumptions that the engineers were making about that profile, and that it was straight lines. Once we had proven what the profile looked like with our geophysical work, the failure plane actually, the credible failure mode actually sat up there. Now, this is a massive bearing in the tailings dam world. I'm not sure if any of you have ever heard of Brumadinho tailings failure, which occurred in Brazil some years back. 280 people almost instantaneously lost their lives through that tailings dam failure. And it brought about a whole set of new rules on how you look at tailings engineering globally. And if any mining house wants to ensure their tailings facility, they have to abide by those rules. One of the things we have to do is we have to predict what happens if a tailings dam fails. So we have to look at the downstream profile, we have to look at the rivers, we have to look at where the tailings would go. We have to come up with two main parameters. First is something called PAR, which is persons at risk, and the other is PLL, which is the potential loss of life if the tailings dam fails. Now, if you don't understand your foundations and you've made up a whole bunch of assumptions about the geology, most tailings engineers know an incredible amount about that bit up there and absolutely nothing about the geology at the bottom. But if you do a dam breach assessment and you try and identify who's at risk and who could potentially die if this thing fails, and you have a failure plane like that, as opposed to a failure plane like that, you are essentially killing a hell of a lot more people just because you didn't understand the geology and the foundations. The rules say that you have to go out there if you've identified people that could potentially be killed with the tailings dam failure. You have to go and speak to them. So if you are using that failure plane as opposed to the actual credible failure plane, in this particular instance, the mining house was speaking to 3,000 people more than they should have. Now that we've proven that the failure plane actually sits up there, they should only have been speaking to about 120 people. And now they have to go and try and unspeak to 2,800 80 people, which is practical impossibility. Most of those people are not highly educated. They were told one day that they were at risk, and now we're coming to tell them, oh, no, you aren't. So this purely stems back to the engineers not understanding the geology in the context of the project, a pretty significant thing. At the time, we were talking about R1 billion buttressing around this facility to stabilize it. And the social engagement side of things just didn't go well on this project. It would have all been much better if the engineers had given a little bit of credence to the geological setting. So, going back to the a priori philosophy of looking at geotechnics, you have to plan your geology, your geotechnical discovery in igneous rocks. You have to understand the shape of what igneous rocks do. You have to understand the way water flows within that. You have to remember how it was formed. You have to understand that there are tools at your disposal, like geophysics, that can help you actually work out what the shape of things look like below the surface. This was more of a technical nature. When you've defined what things look like below the surface and you start placing loads on the surface, there are huge disparities in terms of how the rock behaves. One of them is when an earthquake arrives at surface. So when an earthquake arrives at surface from deep down, it starts a little bit of shaking. If it's in hard rock, it doesn't amplify at all. The minute it gets into softer rock, it starts amplifying like crazy, which is why there's classic photographs of big cracks in the surface of the earth after an earthquake. It's because of that effect. So understanding the geology of a site is rather critical in terms of earthquake loading. So this was just a message to the younger engineers about at least knowing that they're in an igneous rock setting, and how it formed, and that depicting igneous rock in a geotechnical profile as straight lines is just not a good idea. Just checking how I'm doing for time. I'm going to go a bit faster because I'm running a bit behind. So metamorphic rocks, essentially metamorphic rock is initially rock is developed in an igneous setting by magma. It gets eroded, etc. It lies somewhere and gets pressure on it, becomes sedimentary rock. And if it gets back in contact with something hot, it becomes metamorphic rock, where pressure and reheating of other rock changes its character. So you start getting slate from shale, schists from various parent rocks, gneisses from granite, marble from limestone. All of these require pressure and heat, quartzite from sandstone, and you start getting what you call metamorphic rocks, which these are a couple of classical pictures of metamorphic rock. Sometimes metamorphic rock is non-foliated, but generally it's foliated. And then the case study I'm going to present to you is more linked to the crystalline nature that develops in metamorphic rocks. So quartz is one of the most common minerals in rock. It has the lowest melting point in rock. So the minute rock gets reheated, quartz starts flowing first. And so you get a lot of crystallization in a metamorphic setting. I suppose in lay terms, when you drive through a lot of road cuttings, you see these big white lines in the cutting. Those are essentially joints in rock that filled with quartz when the rock got reheated, because quartz flows first and fills all those gaps. But the case study I'm going to show you now is essentially looking at this recrystallization that happens in a metamorphic setting and what that can do in terms of geotechnics. So this case study is at the Namakwa Sands mineral operation on the west coast near Brandsebaai. That's Brandsebaai. If anyone ever camped in their life, they may have found themselves at Brandsebaai campsite, which is over there. This is a mineral sands operation. It's a massive operation. suppose from that side of this is looking down on it, from that side of the pit to that side of the pit is a good couple of kilometers. So this area was mined out, and the tailings dams are actually developed within the mined out area. And as the mining is progressing in a southerly direction, they mine to about 40 meters deep, and the tailings dams follow them. What's interesting in this context is that because it's such a water scarce area, they use seawater as processing water. So the borons and the total dissolved solids and the salts and everything that come from the seawater actually classify this tailings as a type 3 waste. And in the South African context, that means there's a liner required when you dispose of this waste. And if you look at the geotechnical or the geologic, the physical setting. So this is a bit of a zoom in of that part of the open pit. These little features you see over here are where they were chasing some higher grade ore. But the difference between that little feature over there and the bench next to it could be 10 or 12 meters vertically. So if you think about putting a liner, an HDP, high density polyethylene liner into the setting, which is a plastic membrane, how do you do that in this setting? So we were faced with this challenge. It was a type 3 waste, and the regulations and the authority said, line it. So I took a step back and I said, but listen, we're in a metamorphic setting here, and using the Brink books and the like, did a bit of research. Hell a lot of crystallization. So the site I'm talking about, those blue lines over there are the tailings dams. That's the actual mine site over there. I said to myself, well, if there is a waste that's permeating into the ground, who is it going to impact? And can we prove that it won't impact anyone? So if I was in a different rock setting, like an igneous rock setting, where I know that there would be a lot of flow, I perhaps wouldn't have gone this route. But this is a cross-section through the tailings facility when we were designing it. That's the sea over there. This is inland. So conceptual model is that you get rain inland, water flows from inland towards the sea. The groundwater flow direction is always generally towards the sea. We knew we were going to be putting this tailings facility up in this area, and that we would get downward percolation of processed water through it. And we needed to look at the fact that the metamorphic rock setting was not going to allow a lot of flow through it, and who would it impact? So we took a bit of a chance, and we did a set of extremely detailed groundwater flow modeling models to predict what would happen whether we had a liner versus not having a liner. So this set of, once again, those are the tailings facilities to orientate yourself. This is electrical conductivity, which is essentially a signature for the salt coming from the seawater and how that impacts the waste or the waste stream. And this is the development of the tailings facility, compounded by all the other tailings facilities that are in the line, and how that would expand over time. In 2 years, I think this was 20 years, this is 50, and that's 100 years. So that would have been what the contamination profile would look like with a liner, and that's what it looks like without a liner. I'll toggle through them again. That's with liner, without liner. So we could prove quite substantially, because we calibrated these models by drilling boreholes and showing that we knew where the groundwater table was, and we knew that the model was predicting it accurately and the like. So we could prove that there was no impact to any users, and we were able to get away with not lining this facility, which saved the client, I can't tell you how much money, but north of 100 million. So yeah, metamorphic rocks. They're generally a low permeability rock setting. Geotechnics and water is a big thing. Water is an extreme influence in geotechnics. So understanding metamorphic rocks, we could have done that project and smoothed out that pit base at massive cost and lined it. But we were able to do it another way by understanding the geology. We had a very, very sophisticated model, which did take a lot of effort and a fair amount of money, but a hell of a lot less than lining the facility. Yeah. I went through metamorphic quite quickly because of time. So yeah, this was just a message to the younger engineers. Remember how metamorphic rocks forms. It's a recrystallization. The flow paths in the rock get clogged up, get plugged up. So water can only flow through lineaments, something that happened after, like faulting afterwards, etc. Right, let's get on to the interesting one, which is sedimentary rock. So essentially rock that forms from eroded material that gets compressed back into rock. So in the context of this case study, it's a site, it's the Taspin potential nuclear site near Oyster Bay, Cape St. Francis. The tectonic setting is important. When Gondwanaland broke up, there was first an extension, so the continents drifted apart, and then they came back at each other, and they collided with each other to create the Cape Fold Belt, and the site is within that zone. So that's the Cape. Everybody's heard of the Cape Fold Mountains. So those fold mountains developed because there was after the continent breaking up and shifting southwards, it came back at Africa and bumped into it. And if you imagine taking a tablecloth and pushing it together with your hands, you get a fold. That's exactly what happened here. And the Taspin nuclear site is down there next to Oyster Bay. So it's pretty firmly within the Cape Fold Belt. Right. The trusty geological map. I do admit this is a nuclear site. A word on nuclear siting, the extent of engineering that goes into the extent of effort that goes into nuclear engineering is way more than any of you have ever experienced. I can promise you that. The amount of money that gets thrown at it is quite incredible. So this geological map is extremely detailed compared to what I would be able to lay my hands on in a mining setting. So a lot of work has gone into the understanding the geology of this site. And if we look at it in cross section, remember it's the Cape Fold Belt. That's the geological sequence. We're talking about the Table Mountain group. The Peninsula Formation is Table Mountain. The potential nuclear site near here, which is Pearly Beach, is in the Peninsula Formation. But it folds up into the Cedarburg Formation above. Used to be called the Chanda, which is now Gradini. The Kocher is now called Skurverberg, and the Baviaanskloof. But the site is over there. And in geological time, it was folded like that. The surface is now over there. So this bit here is eroded off with time, and the site is left there as a wave cut platform. And when you zoom into it, it's got this geological sequence that has been tilted over with the faulting. And importantly on this site, that there was massive overburden sand over the top of it. So there's a scale issue here. Sorry, I had to blow that up. So the quality is not very good, but that little bit you see at the top there is up to 60, 70 meters of sand, with these geological units dipping down towards the south. When you look at the site, this is the nuclear site over here. This is Taspin, the site being called Taspin. So you have the Skurverberg, used to be called the Kocher at the bottom, the Gradini, or used to be called the Chanda, the Cedarburg, and the Peninsula. That's what Table Mountain's made of. And the Pearly Beach site near here has got that geological feature. And something we discovered was that there was quite a big transition zone between the Overberg and the Gardini. But the point I wanted to make here is that the Brink books, the series, the volume of 4 books I mentioned earlier, had a plethora of information about this geological setting, down to the fact that rotary core drilling in this material is a challenge. There's poor core recovery. You need to employ double and triple tube drilling techniques in order to get good recovery, so don't try and do anything else. So I knew I'd learned all of these things before we put a drill rig on site. The quartzitic sandstone is very hard and abrasive. We measure compressive strengths in the peninsula and the Overberg formations of up to 300 megapascals. Concrete in high-rise buildings is specified at about 40 megapascals. So orders of magnitude stronger than concrete used in high-rise buildings. The rock has a low RQD. It's a geotechnical phenomenon I'm not going to go into here, but essentially the Brink book said drill past your founding levels to understand what's going on. The Brink book said consider incline drilling, and then it said be careful of the variability in sedimentary rock. And it gave a whole lot of other stuff that wasn't relevant to this project, but a whole lot of information exists to us engineers before we even set foot on site. How am I doing for time? Running a bit behind. I'm going to speed up a bit. Initially, there was some work done by the Atomic Energy Commission. Those are borehole locations. When we got involved, we did that drilling in a phase 1, then we did some more drilling in a phase 2. Then we did some shear wave velocity profiling of the site. Some of these boreholes were pushing 200 meters deep. That's very deep for a geotechnical hole, not so deep in an exploration context, but for geotechnical drilling, extremely deep. Then we did some geophysics, we did some hydrogeological work, and we gathered a massive amount of information on the site. This big glob you see over here is an indication of how remote and inaccessible the site is. We just, without helicopters, we simply weren't going to get a drill rig in there. All right, so the Brink books had told us that this stuff is more competent, and that stuff's more competent, and the intermediate, the Cederberg and the Gardini, is less competent. Once we'd done a whole lot of work, if you look at the uniaxial compressive strength of the Overberg and the peninsula, you're getting a mean compressive strength of above 100 megapascals. In the Cederberg and Gardini, it's way down at somewhere near 25, which is stuff that I knew before we got onto the site. If you look at some other properties, this is highly technical, but if you look at elastic properties of the material, it's the same thing. This stuff and this stuff is much more competent than that. This is now the proof of that. That is Poisson's ratio, which is a property that you use to predict how rock will deform. And these are Young's modulus, once again, proving exactly what the Brink books had actually told us before we got onto site. So this is a cross-section through the site after we'd done all the drilling. And one of the main findings of this investigation, so we knew from Brink, and once we drilled that so that's the Overberg, that's the transition, that's the Gardini, Cederberg, and Peninsula on the site. What we actually discovered was when this all eroded off, that there were depressions, a whole bunch of depressions that were eroded into the softer stuff, the softer intermediate stuff, and it filled up with massive sequences of cobbles. So when you walk around, when you're doing your exploring of rock pools, the rounded cobbles you see in the rock pools, this is a fantastic deposit of those rounded cobbles, which had a great bearing on the outcome of this project. Because those cobbles all manifest in this softer zone in the middle here, And these are groundwater contours. We did some very detailed groundwater modeling here. But the groundwater flow comes down from inland towards the coast, and it hits this cobble zone, and you can see it just does a sharp left-hand curve and starts filtering out into this bay because of the transmissivity of this cobble layer. Now, remembering that a nuclear power station needs to get founded on rock because of the earthquake risk, they have to go through about up to 40 meters of soil here. They have to make a massive excavation here if they ever develop this site, which means they have to control the groundwater, which means they have to put in grout curtains or whatever it may be. And the presence of this cobble layer here will actually be the biggest challenge on the site, because you can't put a grout curtain through that. There'll be some pretty sophisticated design work that has to happen on the site. So just showing how understanding the geological setting can help you in a project. You know, looking at the geological maps and BRINC and the work that the Atomic Energy Commission had done previously, it said, be careful of variability, be careful of drilling. I've never, ever had a driller moan as much as they moaned on this site. I mean, it was, the drilling conditions were very trying. It was tricky. But in any case, going through the whole the geotechnical motions, the stuff that we could postulate up front actually panned out. So we knew that there was going to be a variance in the geotechnical parameters. We knew that there was going to be terrible wear and tear on the drilling equipment. There's potential for a tunnel at the site. The cooling water might be brought in with a tunnel, which means they'll need to use a tunnel boring machine here, and that thing is going to get chomped up by this geology. And we discovered some other things. We didn't realize that the site soils would be so homogeneous. That was a discovery. The cobble thing that I've just spoken about was a really insightful thing. And also that the geological setting influences the geomorphology. So no project is done purely on a technical basis. There's an environmental aspect to every project. Geomorphology is very important in a nuclear context. There've been some nuclear incidents on the globe that have been linked to geomorphology, moving sand dunes and the like. So just the fact that those cobbles dominate this area here, this portion of the dunes is permanently saturated, so they never move, and it's an important aspect in terms of the nuclear site risk assessments that are done. We know that these dunes won't move, so they're not a risk, but it's linked to the geology. And in fact, if I go back, the actual formation of this bay, Tace Bay, is there because this geotechnical unit here is softer than the ones on either side. So that's actually how this bay developed in geological time. So sedimentary rocks, important thing about sedimentary rocks is the variability, particularly if those rocks have been turned over, like in a folded setting. And you've got to expect that there's going to be variability. From a geotechnical perspective, developing across geological units with variable profiles is a challenge. But these are things that you can actually know before you get to the site if you lend a little bit of credence to geology. That's my say. Any questions? Welcome.
So just a quick one. I really do have a soft spot for drillers. They all have to quote on their operation, and they're basically working on your power method. They go on previous experience to quote. So just a question on the drilling that you mentioned from the nuclear side. Did you review their quote per meter? Or just
No. We gave them a lot of information up front. We said to them, be careful.
Just perhaps qualify.
Oh,
yeah, just paraphrase.
So the question is, did we have difficulty with the drilling quotes, etc., at the nuclear site and Tastement, considering the difficult drilling conditions? So we gave them a lot of information up front. We told them that there'd be massive wear and tear on their drill bits. We told them that there would be a series of vertical joint sets that would fall into the borehole so that they'd have to case. So when they quoted for all the necessary aspects. But it was a trying drilling project because the water table is extremely high there as well. So the tendency for draw holes to collapse and all that type of thing was very high. So we made sure that they had very robust casing priced into their drilling program. Yeah. Yes.
I'm curious about the attachment thing. It sounds to me like it's actually not the ideal spot. Am I missing something?
No. So look, I'm a technical beast. I don't know. I don't get involved in South Africa's energy mix, but what I can tell you is I want to get to a map. Oh gosh. Okay, so the question was, it sounds as though Tasman is not the ideal setting for in a nuclear context. The one thing you need to understand in South Africa's energy mix is that South Africa's challenge in terms of power is not as much generation ability as it is a mix between generation ability and grid stability. So all of South Africa's power gets generated at Overberg, down near Cape Town, and up in the PWV area in the coal fields. So those are the two main areas. That exposes the eastern half of the country quite significantly, because if you take Overberg down to do maintenance, it's very difficult to get the power everywhere else in the country. So Eskom's challenge of late has been one related to maintenance. They can't take Medupi or Kusile up in the PWV area down and do proper maintenance on it, or take Overberg down and do proper maintenance on it. So the preferred nuclear site, and I encourage you all to go and read the environmental impact assessment, which is on the Eskom website. The preferred nuclear site is actually the Tasman site. The reason being that they would like to triangulate the generation ability so that, for example, if they ever developed the Tasman site and it was a significant contributor from a generation perspective, they could actually take Overberg down properly and do proper maintenance. They could take Medupi and Kusile down properly and do proper maintenance, and they wouldn't expose KZN and other areas because the power grid would be triangulated. Maybe just because you're from this area, the Pearly Beach site is not high on the hit list in Eskom's plans, mainly because it doesn't provide them with this triangulation ability. And also the cost of the nuclear power station is maybe pushing just more than half of the cost of the project. The major cost is actually in transmission and buying up of all the land and all that type of thing. There are actually two nuclear sites up the west coast here, Brazil and Skulpfontein. But the transmission costs from those sites to, for example, Johannesburg, just screens them out. They're not viable. So Tasman is actually the preferred site. If you read the environmental impact assessment, and if you read the South African authorities' take on the environmental impact assessment, they actually authorized the Danafontein site, which is right next to Overberg. So if the energy mix includes nuclear in the future, Eskom will probably revisit the EIA and try and push for that site, because if they can triangulate this generation, it would solve South Africa's energy challenge.
And can I just add there, I mean, we're talking here base load.
Yes.
And I think there's a huge problem in this country and the world for that matter. If you're going to run industry and households and get kids to the school in the morning, you need reliable base load. You know, green energy and all of that stuff, and the stuff up in the Macqualand, the wind farms and the solar is great, but you've got to have reliable base load. And I think that's something, you know, we miss in this country.
Okay, so do I get you correctly? the actual site location, the decision has been made because of the strategic positioning and not really because it's a suitable geology.
No. It's so the question is Tasman being aimed at because of its geographical position, irrespective of its geological setting? And the answer is no. So I think one of the most impressive things I've seen in my career was the seismic hazard assessment that was done for the Tasman site. It was done by a group of maybe 40 people from across the globe, led by someone from Imperial College in London, which is the epicenter of geotechnical learning in the world. And an excessive amount of work was done in looking at the seismic hazard assessment for Tasman, much more than was done, for example, for the Overberg site. So it is a suitable site. Eskom will have to go through whichever motions they need to look at it again. I don't know what the plans are in terms of South Africa's energy mix. There is a huge amount of renewable work that is going on in that area. So around Jeffreys Bay and the like, I think SRK has done possibly 30 projects, renewable energy projects in that area, either from an environmental or geotechnical perspective. So there is energy. There's a huge energy mix in the thinking in South Africa. What Eskom's plans are going forward, I'm not sure. My job is to make sure that we understand the geotechnics.
And just to add on the geology there, and to answer Anton, I mean, that geology is the same geology as these mountains behind us. And although your diagram suggests, that those rocks in the middle are somewhat less competent, they're still incredibly competent sandstone rocks.
Yeah, so look, the viability of the site comes down to the seismic hazard. Like, so the rock quality and whatever is a factor, because you have to understand that an earthquake comes from deep, and it gets amplified as it comes up to surface. So you have to understand the geotechnical profile. But the more important thing is understanding the sources. So where would an earthquake source be? And that was studied in great detail. The other aspect that was studied in quite great detail was tsunami hazard. And our closest source of tsunami is the South Sandwich Islands, which is down near Argentina, down way down south. So tsunami is not such a big aspect here. We do get meteor tsunamis. So there's meteorological phenomena that develop tsunamis, but they're not as dramatic as the earthquake-induced tsunamis. The amount of effort that goes into nuclear engineering is quite impressive. You must remember that a nuclear project in South Africa is not a South African project. It's a global project. It's watched by everyone. The Atomic Energy Commission's on top of it. The rules and the guidelines that are used so we're only looking at the site safety aspect of it at the moment, but we have to follow the US National Nuclear Regulatory Commission's guidelines. All the design has to be done probabilistically. You have to factor in uncertainty. It's extremely tightly watched from a technical perspective, and the whole nuclear industry is based on a lessons learned aspect. So for example, when the tsunami hit Japan, Fukushima, we were under extremely tight deadlines on these projects to get stuff done. We were stopped, and all attention was given to tsunami risk for a while. So the nuclear industry is very heavily lessons learned. If anything happens anywhere, it doesn't matter what the accident or incident or near miss, it reverberates through the entire globe. So yeah, it is one of the aspects about nuclear power engineering is that it's not a local project. it's got many eyes on it.
And just to add too, I mean, the beauty of Africa or Southern Africa is the geology and the seismic hazard is actually quite boring.
Yeah.
And you know, our biggest seismic activity is actually around the Wits Basin, the Pacific Coal Mine.
Mining induced, yeah. So it is rather seismically inactive. So it's a stable continental area. The risk that is factored into, and I encourage you to read the EIAs. It's explained in there. But the main risks that were factored into this was knowledge of offshore faults. So it's easy to go and find the Congo-Bavianes fault and dig a trench into it and measure how much it's moved over time and all of those types of things. I mean, they're fantastic techniques in doing that, and you can get very accurate. But what is the source characterization look like offshore, etc.? So that those types of uncertainty had to be factored in. It's a very interesting science.
Question: the geological difference between Tasman and Pearly Beach in terms of suitability for nuclear site?
Can't really be answered that question because Pearly Beach has not been subjected to the seismic hazard analysis that Tasman has. So Overberg and Tasman have undergone full seismic hazard. It's an interesting concept. That it's called SHAC, Senior Seismic Hazard Assessment Committee. Essentially, there's a group of people like me that do the work, and then their competitors sit as a peer review committee and pull the work apart. So there's a series of workshops that you go through and you present your work, and there's experts that try and trip you up. So you can't take any shortcuts. There's no shortcuts in nuclear engineering. One of the workshops, for example, is open to anyone. So, for example, if you're proposing a nuclear power station at Pearly Beach, and there's one of you were a seismic hazard expert, one of the workshops that you go through is that you can go there and try and rip them apart with your own theories and the like. It's an extremely interesting way of going about a project, but very, 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 very watched from the outside. No shortcuts allowed.
Katie?
Just, I saw the set of northeast trending joints in the sandstone basement. Was that included in your water modeling?
Yes, indeed. You mean from this map?
No, from the plan, from the
blow up you showed.
The zoom in on the satellite image there.
Yeah.
So you can see the northeast trending set of structures on the beach.
Yeah. No, absolutely. So look, this was all extremely closely mapped. I mean, this entire coastline. In fact, it was very closely mapped from here to Nature's Valley, and beyond Port Elizabeth. So every wave cut platform was mapped in a lot of detail. They took a lot of samples from those areas to carbon date them to see wave cut platform levels relevant to each other and the like. It was a very interesting study.
Okay, but the joints would be like in the basement of your pebble bed.
Yes.
So that would be completely different permeability.
Yes. Yeah. No, absolutely taken into account. You must remember that every single borehole we drill here that we drilled here has a piezometer in it. So we're monitoring wrong way, sorry. So all of the groundwater modeling that we've done is very, very closely calibrated. Sorry. So all of these boreholes have got piezometers in them. There's probably about 180 boreholes there, and the groundwater model is compared to the actual measurements And we've got data loggers in a whole lot of them. So we're getting a reading every minute. We're taking data every minute on this site.
And just to add to that, I mean, some of you have listened to Hayley Cawthra previously talk here. She's a wonderful young geologist, works for the CGS in Belleville, Cape Town. She's been involved. She doesn't talk about it, but a lot of it's still confidential and all this work. And again, what Bruce is saying, the detail of mapping, every joint, every fault, every place that, rock can break is quite incredible. And there's a young lady, and to me, she's one of our best young geologists around. But when you look at the quality of that work, and Bruce has highlighted that again, it's quite phenomenal.
So
at the back.
On the maps, are any of these maps open file?
Of the nuclear site.
The mapping that they've done, for example, what Don is talking
You'll
about.
see
Yes.
Yeah.
So you if you go and look at the EIA, one of the appendices is the geology, which was done by the Council for Geoscience. Another appendix is mine, the work I did. There's 15 technical chapters that go through water supply, marine engineering, geology, seismics, geotechnics, hydrogeology, ecology, geomorphology, demography and emergency planning. And then there's, of course, in the nuclear context, if you were to consider, for example, putting a nuclear power station on this site, you have to go and understand what the entire human food chain dynamics are in the area. So this for example, the Tasman site is slap in the middle of South Africa's premier milk producing area. So you actually have to calculate what radiation release would look like in terms of production of milk and that milk getting distributed around South Africa. So there's extremely in-depth and detailed demographic and contaminant transport studies done. Read the EIA, it's a couple of 1,000 pages long, but
it's all there. I mean, I think sadly, and that's we all sort of head to, we all have this impression that the state in South Africa is broken, gone, buggered. But when you actually go and look below that and see some of the work that goes on studies like this, it's incredible. And credit to our people. Alpha, yeah.
Bruce, thanks for the presentation. Have you any comments on the Free State disasters by
Very spread.
design or trade maintenance?
No. So, look, Mary Sprat was an overtopping incident. It was a low probability incident that happened. So there was additional deposition and then a massive rain event and so a whole calamity of things happened. The Brumadinho case that I mentioned earlier, the one in Brazil, was essentially a case of the tailings dam was no longer being used. They took their eye off it. So there are 5 people in jail now because of that failure.
PhD.
That was Varley. It was a Varley site.
Yeah. And then Jagersfontein, Diamond.
No, I don't know anything about that one.
I think again, probably neglect. And there was actual 24/7 surveillance on it as well.
I was involved in a project in 2010. We still contain the tailings dams and to be moved. Because I provided a lot of the chemical background to actually those tailings dams in Malta. But then I thought that the project was doing other work. But I can't remember what happened. Do you remember what happened when we were tailings dams?
No, I actually haven't worked on any of the gold stuff yet. But the standards that I said were developed after the Brumadinho failure have a very strong geochemical component to them. You have to understand the geochemistry of the tailings.
One problem there was the acid drainage dissolving under the contact that we.
Indeed. So today, if you want to develop a new tailings dam today, you actually have to understand the geochemistry of your tailings. You have to understand long term what its reduction potential is. So is it going to reduce down? Are there sulfides? Are you going to drop the pH in your water? So the minute you drop pH in groundwater, all metals go into solution, so your contamination profile gets bigger, etc., etc. So you have to understand all of that. And that's why I half hinted at the type 3 waste needing a liner, etc. You have to prove that you don't have a waste like that. And you have to go through the geochemical side of things. And there's prescribed tests that you have to do. You have to do leachable potential tests, contamination, leach potential tests, and all sorts of things.
Okay, I think we can draw to close. Bruce is not rushing off in an immediate hurry. People can talk to him. I'd like to thank you and compliment you on your geological skills.
Thank you for listening.